Some of the additional characteristics of projectile motion is left. As of now, we have completed 80% of the chapter. Some of the additional characteristics of projectile motion is left. So in this video, we'll discuss these characteristics which are very useful and interesting. So we'll start with the range and time of flight. So consider a projectile is launched at some angle above horizontal with speed v0, and this is the trajectory of the projectile. Also, the initial and the final elevation is same. This is the initial elevation at time t equals to 0, the elevation y is 0, and the projectile returns to the same elevation, this is y equals to 0, at some time t. And the horizontal distance traveled by the projectile is what we call the range of the projectile. So this will be the range of the projectile. We represent it with r, the horizontal distance traveled by the projectile. Now let's figure out the expression for range, and for that we're going to use the fundamental equations of motion. So first we'll find the time when the projectile lands after launching, and for that we're going to use this equation: y is equals to y0 plus v0y times t plus 1 over 2 ay t square. These are fundamental equations of motion in the y direction, and the acceleration due to gravity is downward, so ay will be minus g. Now this is the initial position of the projectile, so y0 is at origin, so this term is 0, so this will be y equals to, now the y component of this velocity will be v0 sine theta, so we can write this is v0 sine theta, this t as it is, plus 1 over 2. Now this ay is minus g, so I can write minus g t square as it is. Now we can equate this y equals to 0 to find the time when the projectile lands after launching. So this equation becomes v0 sine theta times t minus 1 over 2 gt square is equals to 0. From here we can take t common, so t is common. We can write v0 sine theta minus 1 over 2 gt is equals to 0. So from here we can write that either t is equals to 0 or v0 sine theta minus 1 over 2 gt is equals to 0. Now what this t equals to 0 represents, that at t equals to 0 the elevation is 0. So this is the first time when the elevation is 0. Next, when the projectile reaches here, the elevation again becomes 0. For that we can use this equation to find that time. So from here we'll get that t is equals to 2 v0 over g sine theta. So this is the time taken by the projectile to land after the launching. Okay, but our aim was to calculate the range. So for that we're going to use the fundamental equations of motion in the horizontal direction, which is x equals to x0 plus v0 x times t plus 1 over 2 ax t square. Initially the projectile is at the origin, so x0 is 0. In x direction there is no acceleration, so this whole term is 0. Now what here x represents? The range. This is the x, that is the range. So we can replace this x with r. R is equals to v0 x. Now x component of the velocity will be v0 sine v0 cosine theta. So v0 cosine theta times t. T we have already calculated to be 2 v0 over g times sine theta. We can simplify it further and we'll get this is equals to, okay, let me write here, this is equals to v0 this V0 and this V0 becomes square, so and this 2 as it is over G sine theta cosine theta, and we can use one trigonometric formula here, which is sine 2 theta is 2 sine theta cosine theta, or we can write that sine theta cosine theta is sine 2 theta divided by 2. So we can replace it here. So that will be equals to 2 V0 square divided by G, and this will become sine 2 theta divided by 2. This 2 and this 2 will cancel, and finally we'll get the expression for R to be V0 square over G times sine 2 theta. So this is the final expression. Now this expression is valid only when the final and the initial elevation is same. Otherwise this expression is not valid. Now if you observe carefully, we see that here R is inversely proportional to G. You can write that R is inversely proportional to G. So as the value of G decreases, the value for R, that is the range, will increase. For example, a projectile launched on the moon where the acceleration due to gravity is only about 1/6 on the earth, so it will travel about 6 times as it would have on earth, which you can see in this video. I missed out one thing. This time is what we call the time of flight, the time taken by the projectile to land after launching, and this expression is for the range. Now let's take an example on it. So this is the example, and it says that a football game begins with a kickoff in which ball travels horizontally of 37 meter. So this is basically the range that we are given with. Range we are given as 37 meter and lands at the same level. So we can use the expression that we have derived just now. If the ball kicked at an angle of 44 degrees above the horizontal, what was its initial speed? So we have already obtained the expression for range, which is R is equals to V0 square over G times sine 2 theta. And from here we can write that V0 square is equals to RG over sine 2 theta, and this square would become under root here like this. So V0 is the initial speed, so we can use this expression to find the answer. So V0 is equals to under root, R is 37 meter, G is 9.81 meter per second squared, divided by sine 2 theta. So sine 2 theta is 88 degrees, and on further solving we'll get the answer to be 19 meter per second. So this is the initial speed with which the projectile was launched. So we have derived the expression for range. Now think how we can maximize the range of the projectile. First case, either we can increase the initial speed V0. If we increase V0, R will increase. Second way is to change the angle theta. Angle theta here is the launch angle. So now try to figure out at what launch angle the range is maximum. Now the range will be maximum when sine 2 theta is maximum, and the maximum value for sine 2 theta is 1. At what angle sine 2 theta would be 1? We know that sine 90 degree is 1. That we can say that 2 theta should be 90 degree, or we can say that theta should be 45 degrees. So at theta 45 degrees, sine 2 theta will be 1 and the range will be maximum. So second case we can write that theta should be 45 degrees. So in this case the maximum range will be given by the expression V0 square divided by G. So this is the expression for the maximum range. Now one thing you should remember, that this expression is valid only when final and initial elevation is same. But what if the elevation is different? Let's discuss that case also. So here you see that here the projectile lands at a higher level, the elevation is different, and here the projectile lands at the lower level. So in both the cases the elevation is different. So the case in which the projectile lands at the lower level, the angle for the maximum range is less than 45. If theta is less than 45 degrees, then the range will be maximum. And for this case, when the projectile lands at a higher level, like here it lands at here, which is h height above the initial height, so we can say in this case theta should be greater than 45 degrees. Finally, this expression is valid only for the idle case. Idle case means when there is no resistance, no air resistance. Now let's discuss what would be the effect of air resistance. Now in case where air resistance is significant, for example the flight of a rapidly moving golf ball, the maximum range does not occur at theta equals to 45. In such cases, maximum range occurs for a launch angle less than 45 degrees, and the reason is that with a smaller launch angle the golf ball is in the air for the less time, giving air resistance less time to effect its flight. So projectile with air resistance, in such cases the maximum range occurs at theta less than 45 degrees. And I've also represented the range of a projectile with same initial velocity but with different launch angle. Like here, this is the range of the projectile when theta equals to 15 degree. This is theta equals to 25 degrees. This is theta equals to 35 degrees, and finally this is theta equals to 45 degrees. So here you can see for theta equals to 45 degrees the range is less as compared to the range for theta equals to 35, because we have considered the air resistance, and for such cases the maximum range occurs for less than theta 45 degrees. So this is all with this video, and in the next video we'll discuss some more characteristics of projectile motion. Thank you.